Hi, this is Surely Physics, episode on force diagrams, also called free body diagrams. We're going to be looking at ways that in physics you look at objects and scenarios and try to simplify them down to what matters. And usually what matters is forces. Forces are what change motion. Forces cause acceleration. So even something as simple as pulling a sled through the snow, there are different forces at work which make it easy or difficult and sometimes even fun. Um, we're going to be looking at modeling objects and throwing away everything else that's unimportant. That's why it's also often called a free body diagram. All right, in the first slide here, let's take something standard, a dresser. So when you're thinking about a dresser, and let's say you want to push your dresser around a room, you're reorganizing your room, I want to move my dresser. It's not always easy to just draw a finely tuned dresser. So oftentimes what we're going to do is, instead of thinking of the dresser as this ornate object, that doesn't really matter when you're pushing the dresser. You're just pushing these objects. So let's throw that aside and just think of it like a box. So generally, if you've got something that is not rolling, you'll draw a box. This is a dresser. If it is something that does roll, you might draw a circle. So here we have our dresser. Now, there are forces that we're labeling around it. Pulling it down, what do you think that force is? Fg, force due to gravity. And force due to gravity is also called weight. Weight is that gravity that always pulls downward. So in addition to this line, we can add an arrow to that end to show it's a downward kind of a force. All right, but as you notice, I'm only labeling forces. We're not labeling velocity or inertia or even acceleration, just forces. And that's what's going to be important here. That's what we're going to use to apply Newton's second law to determine things like acceleration or velocity later on. What about FP? Well, sometimes you've got these applied forces. The scenario says the dresser is being pushed across the bedroom floor. So applied forces like a push. And in this scenario, I guess I'm pushing it to the right. The push are labeled with the most descriptive and obvious labels possible. So you might have a push, pull, thrust, throw. There's a lot of different things that could be an applied force. What about Fn? Fn is something we're going to talk about later with my course. It's a normal force. A surface, a flat surface, has a direction to it. Whatever direction that its surface faces, which is perpendicular to that surface, is called the normal. It's often a mathematical term. You also use it in optics when you're thinking about the normal to a surface, when you're thinking about the angle of reflection. So angle of incidence equals angle of reflection. It's all compared to that normal. But a normal is just a direction that is exactly perpendicular to a surface. So the normal force, this is the upward force from like the floor or the chair, supporting the weight of the dresser. And what about this FF? So we've got a dresser that's being pushed across the bedroom floor. This is friction, of course. So that's what makes it difficult to push a dresser. The friction resists the motion of the dresser. It works opposite the pulling force. So if the push or the pull is to the right, then the friction is to the left. All right, so that's just a basic brass tacks piece of it, what makes it up. So here's a new example. A child sleds down a hill. Now in this one, we've got an angle. And if the child's sledding down a hill, what's pulling the child down? It's not like an engine or a motor or somebody pushing the kid. It's just gravity. So in this kind of scenario, it might look a little weird. There's the downhill slope. Sometimes on a force diagram, if there is a slope, we're going to put some kind of line or reference point. So that's what we have here is the slope, is that orange line. You might put a dashed line if you're drawing this on your paper and don't have different colors. So what is always pulling down toward the center of the earth, no matter if there's a slope or no slope or a vertical surface? Gravity is always, the weight is always pulling down towards the center of the planet. So I'm just going to drag this FG up here and got a little ding. I must have gotten that right. Okay, now what other forces might be involved here? Now a moment ago, you might recall that I mentioned the normal force. So we also have the ground here, but there's no upward force, is there? See, the normal force doesn't just support weight, okay? Sometimes it doesn't support any weight. Sometimes it's working against a pressure or a push. For example, if I was trying to hold a brick up against a vertical wall, I'd push against the brick, and the brick up against the wall would have the wall pushing back. So that wall would have an outward, like a almost horizontal force, pushing force, normal force. So the important thing is the word normal. Normal is perpendicular. So if this is the surface, is the orange line, then the line that's perpendicular to that surface is that normal force. There it is. Now as a kid goes down the hill, what other forces does the kid encounter? Now we got to assume that down the hill is this way. That's the direction a component of the gravity is going to pull the kid. But what are these arrows, or what do these lines here represent? So these would represent resisting forces. So what kind of resisting force is out there? Well, the one closest to the ground, this must be a resisting force due to the ground. So that is probably friction. There it is, we're right on target. So what about the other force here, or this last one? What else could be resisting the child's motion? Well, if the kid's going pretty fast, then there might be another resisting force. The child is also not only moving along the ground, but the child's also moving through the air. So air creates air resistance. In physics, we call that drag. It's a lot shorter word, and it's easier to sum up. Drag also includes things like water resistance and things like that. So any fluid resistance is drag. So that's a more involved kind of scenario. So let's just try one more. If we were to make our own force diagrams here, we got a car accelerating onto the highway. This is where you're generally going to start out. Now the car does have wheels that roll, but the car isn't like flipping over itself. So I'm just going to use a box here to represent the car. Now the car is accelerating on the highway. I guess there's going to be some kind of arrow pushing it forward. Okay, I'm just going to kind of make that. It's a big acceleration, so I'm going to make it kind of a big arrow or big line there. My device is supposed to be showing these arrows. It's not. Whatever. Okay, so that's the direction of that force. Now, this is an applied force. There's an engine here, so I might put an FE for the force of the engine, but a nice general term for planes, trains, and automobiles, pushing force is thrust. So I'm going to use an FT for thrust, force of thrust. So that's an applied force there. Now, it doesn't say this car is on a slope, and if it was specific about that, we'd include a slope, but since it doesn't mention one, I guess we're going to assume this is on nice, flat, level, horizontal ground. So what other forces might be acting on it? I'm going to try some gravity here, and take this arrow, this downward arrow, and cars are kind of heavy, so I'll give it some decent amount of weight, and that's FG, force due to gravity. All right, so according to this force diagram, if this were all the forces that were acting, this car would be accelerating to the right and down into the ground, kind of a diagonal direction. Now that's not the direction that the car accelerates on the highway in. So what else is at work here? Well, besides gravity pulling the car down, what's it sitting on? It's sitting on the ground. The ground pushes back up. So that is a normal force. I'm going to drag another vertical arrow here. But you know what? If the normal force was this long, what would that car be doing? It would still be sinking into the ground. This would be like sinking slowly, accelerating slowly, like through mud or something like that. But the ground is fully supporting that weight. Now, if I made the normal force this big, this would indicate that the ground is launching the vehicle up into the air. Now, it might be kind of entertaining to see that, but generally, the car is being completely supported by the ground. So I'm going to try to draw a line there that's about the same size as the weight force. So these are force vectors. They have magnitude and direction. So the length of the arrow represents the magnitude, the amount. And since these are equal amounts, but opposite directions, we want them to be, the weight works against the gravity. The weight works against the normal force. They're opposites, opposite directions, but they're also equal because that ground fully supports the weight. And it doesn't launch the car up in the air. It doesn't allow the car to sink into the ground. So they should be about equal in size. I think that normal force is just a little long. Maybe not. I'm guessing about right there. So besides this car is moving really quickly. So if you ever roll down your window, and be safe about doing this, but just if you put your hand out the window when the car is moving slowly, you might recall that there's like an air resistance, a push against your hand. Now, if you stick your hand out the window on the highway, watch out for things going by, especially like large bumblebees. they really hurt when they hit your hand. But also larger things can of course hurt, so be safe about this, please. But if you stick your hand out the window on a highway and you're moving rather quickly, you feel a lot of air. So as this car accelerates and gets faster and faster and faster, the air resistance does increase. So I'm going to drag some drag over, and also going to try to get that arrow. There it is. And we're going to make this a little bit longer. Now, something about drag is if the car is going at a constant speed on the highway, which is really possible, right? You can go to, get into cruise control, go constant 60 miles per hour. Well, if you've ever driven a car, if you're going 60 miles per hour on a driveway, you actually have to push down on the accelerator pedal, the gas pedal, slightly just to keep your speed up. So what's that mean? That means you have to continue pushing your car forward. There has to be a continual thrust. Well, if there's a forward acceleration from the engine, doesn't that mean it's going to get faster as it moves forward? But the car actually remains at a constant speed. So whenever you achieve a constant speed on the highway, you got to think that the pushing force of the engine, that thrust, is equal to all the resisting forces moving backwards. Now you might say, oh, what about friction? Isn't there friction between the tires and the ground? Well, there is an important kind of friction. It's called static friction, which we'll get into a little bit later. But that kind of friction is a sticking friction. It's also called rolling friction, where the tires grip to the ground and use the ground to push the car forward. But there's not like a sliding kind of sound. Now, rubber against the road has that squealing kind of sound, and it smells like burnt rubber. So that's not what's happening on the highway. You're just rolling along. So there's not really friction that's resisting the acceleration of the car. Now, there are some internal frictions from like the pistons moving inside the engine heats up. So there's some friction inside. There's some friction within the transmission of the vehicle if it's a gas vehicle. There's a friction of moving parts, no matter what kind of vehicle it is. But if it's accelerating onto the highway, we're assuming here that it's speeding up. So therefore, the thrust here has to be greater than the drag. So I'm going to make the drag shorter than the thrust, just to make sure we have a car that's accelerating. Now, if you do want to slow down, here's what you could do. You could decrease the thrust. And look at that. If the thrust is less and the drag is more, that means the car is going to accelerate backwards. If it's moving forward, it's going to have a backward acceleration, meaning it's going to slow down. So these force diagrams are going to start revealing a lot of information about these scenarios, and that's why we make them. All right, so you can come up with any number of scenarios. Let me try to draw a few here. Let's just take something really simple here. Let's take a block that's being pushed up a ramp. Okay, maybe it's a loading dock. It could be a fishing boat. There's some fishing boats that got to be pushed up the ramp. Okay, just gonna make this triangle a little bit better. Okay, and often with the ramp, there's an angle associated with it. So there's our object. All right, now I've gone a little bit too far. There's going to be some kind of push here. This is not a force diagram. This is not a free body diagram. That's why I'm drawing in red. Okay, it's not what we want to do here. A force diagram would be just the box. Okay, at the most, you might have a dash dotted line to represent the slope. You can even put a little theta in there. Okay, if you have a theta in the scenario, you could write that in. It might be 45 degrees here. All right, but if the box is being pushed up the slope, that means there is a pushing force. And generally, if you're pushing up the slope, you're not going to be pushing vertically upward, but you're going to be pushing horizontal to that slope. And there is a slope here, so there's going to be a normal force, most likely, that's perpendicular to that surface. Now, really, this normal force is originating at the bottom here, at the slope. So it would be appropriate to draw that force diagram arrow from the slope itself. The pushing force is also from the behind here, from the back here. We would label that the normal force Fn. Okay, so what else might there be here? Well, there's also going to be gravity. Now, gravity works on the center of mass of an object, unless you're dealing with a rotating system, which we'll look at later in the course, it does matter where the force is applied to cause an object to rotate. It's applied on the outside or kind of partially on the inside. Does it make it turn? What directions is it applied? So all that's going to come up. But gravity acts on the center of mass of that object, okay, that weight. So there's weight, Fg. And as it's being pushed up the slope, what else might it encounter? It might encounter a little bit of friction. Now friction is applied at the base of that block. So I'm going to put an arrow coming from the base here, and we're going to label that force of friction. So there's just one more example there. And that's how you do this. Like there's kind of a list you should go through in your head. Is gravity involved or weight? Okay, so that's the first thing you think, because most of the time it's going to be involved. All right. How about a surface? If there's a surface, is there a normal force? Okay, so there's a normal force that should be perpendicular. There's a perpendicular sign to the surface, so there has to be a surface involved. All right, other forces. Is there any friction? Friction versus drag. Friction is resisting force between solid surfaces. Is there a frictional force, or is there a drag? Drag force. Now this can be like air resistance. This can be water resistance. Okay, it's a fluid resistance. Anything that flows that's moving through. And then you think, are there any other applied forces? So listen to the scenario. What's going on here? What's making things happen? Okay, so that's generally what you go through. Those four main things. Remember, if you're like, what about thrust? Well, thrust is another applied force. So over here, this thrust and the push, those are applied forces. Here we're at normal force, drag, friction, and gravity. Those mainly are going to get the job done. Many force diagrams will also have values or numbers, and some of those forces that we were just looking at will turn into numbers as we go and develop through this course. So let's take a new scenario here and add some numbers in. What if we've got 20 newtons of weight? I'll just go ahead and label that. Okay, and it's sitting, there's some kind of object sitting on the surface. So there might be some normal force. That's also 20 newtons. All right, now we're just going to push this along to the side. Let's give it 30 newtons of push. And let's say there's either drag or friction involved here. Let's say there's only 10 newtons going this way. Okay, so there might be a push force, and there might be some friction. Okay, so big question, what is the net force? This is a skill that, we're just going to keep doing over and over and over again, and you're going to get good at it. Okay, so what's the net force? Now this is more like a net income. So for example, if you have a job and you make $400 a month, okay, you're not, just starting out here, okay, $400 a month, and you got to pay $200 a month in car insurance because you caused a little fender bender in a parking lot, okay? So your car insurance went up and mom and dad are making you pay for it. Next we got, what about that phone bill? Well, you want the unlimited plans, so it's about 80 bucks. So and finally you're saving a little bit of money for college. Yeah, right. Okay, so out of your $400 a month, but hey, what we're going to save for college. So, and let's say you're going to save about 50 bucks a month. So what's your net income? Well, you got $400 you're making, you got $200 from the car insurance, you got an $80 phone bill, and $50 going to your savings. So the net income would be take your positives and subtract out your negatives. So it'd be $400 minus 2 is 200, minus 80 is 120, minus 50 is 70 bucks. So your net income is $70. Same thing here. All right, what's the net force going to be? And whenever we look at the net force, what we're going to do is we're going to sum the forces in each of the directions. If you recall back to projectile motion, we broke up motion that's in 2 dimensions into the x components and the y components, the horizontal and the vertical. That's what we're going to do here also. What's the net force in the y direction? So this means sum of the forces in the y direction. And we're also going to look at the sum of all the forces in the x direction. Okay, so in the y direction, the sum of all the forces is 20 up minus 20 down. Now, do you see how they're going opposite? That's why I said minus. You're really summing here, so I'll be legit here. You're adding a negative 20. Now, you don't have to write negative plus a negative 20 all the time, but just so you can see, we are summing, and these two forces, the up and the down, are working against each other. Now, if there were two forces pushing up, we would add them together. So what if there was a spring on the bottom and boing, 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 it just added a little bit of force? Well, then we do 20 plus 10 minus 20, and that would give us the net force. But there's no spring. So in the y direction, the net force is a big whopping 0 newtons. What about the x direction? We got 30 newtons to the right, and we're going to add a negative 10 is the friction to the left, and that gives us 20 newtons. And do recall that a force is a vector, so that's 20 newtons to the right. So we have to add on a direction to that. So what's the net force? Well, this one's kind of easy. It's 20 newtons to the right. There is no y direction force. All right. So just to take you through that again, what if there is a similar scenario? Let's say there's a force off at an angle now. Okay, and this force makes an angle that looks a little about 40 degrees or so, and let's call that 30 newtons also. All right, let's say there's a force downward. Let's call this 100 newtons. Let's take a force to the left. I'll call that 10 newtons. Okay. So the question is, what is the net force acting on this object? So this one doesn't have any little components that are going to cancel too well here. So we're going to do this the same way, but first we're going to take a step. We're going to redraw this force diagram, this free body diagram, and we're going to take any angled components and break them up, angled forces, and break them up into their x and y components. So 100 newtons is already in the y direction, so just leave it. 100 newtons is in the y direction. 10 newtons is already in the x direction. Let's just leave it. All right, now are these to scale? Not really. This one should be 1/10 the length of this one, as long as it's longer. 100 is longer than 10. You're in pretty good shape. I usually try to keep the vertical ones relative and the horizontal ones relative too. But this 30 Newton force, you see it's broken. It's at an angle, and we can't really add or subtract numbers that are all kind of off at an angle. So how you want to envision this is this 30 Newton force has an upward component and a right-hand component. Now again, my 100 Newton force relatively should be rather large there, okay? But I just want to focus in on this 30 Newton force right now. It goes up and to the right. I can draw this same arrow right over to the side here. You see how it's the same length in the same direction, but now in this perspective it makes a right triangle. Okay, so this upward component is really the side component of a right triangle over here. And in essence, it's very similar to taking the horizontal and vertical components of a projectile's launch velocity. So how would we figure out these components? Well, on a right triangle, this would be the adjacent side to the 40-degree angle. And what trig function goes with the adjacent? That would be the cosine. Now 30 would be the hypotenuse. It's the length of this vector. So the horizontal component here would be 30 cos 40 degrees. And this would be a force in newtons. With projectiles, if this were like 30 meters per second, then you'd find the horizontal component, that would be 30 cos of the angle, 40 degrees. And the vertical component would be 30 sine of 40 degrees. Likewise, this is going to be 30 newtons sine of 40 degrees. Okay, and that's what we're going to label down here in our new diagram. Okay, but I will make it a little shorter to make it more to scale here. This is going to be 30 sine of 40 degrees, and we'll have 30 cos 40. I don't know how long that one is, so just kind of make it a little bit different from the 10. 30 cos 40. And of course, those have real values. I plug in my calculator here, get it out. 30 sine 40 degrees. I get 19.28. So that was the sine. So this is 19.28. And 30 cos 40. 22.98. So 19.28 and 22.98. All right. So now I got some actual values here. This one's 22. That's about 23. Okay, I'll just call it 23 here. Okay, I'll just call this, just to simplify it a little bit, it's about equal to 19. So 19 and 23. There we go. So what's the net force? Well, we're going to sum the forces in the x direction and the y direction. I'll start with x here. I always like taking the bigger one. It's really arbitrary which way is positive. I'm going to define right as positive. And you know what? Let's have fun. I'm going to also define in the vertical direction down as positive. You can make them either way. As long as you've got those two perspectives, whatever answer you get out will be in terms of these directions. So in the x direction, I have 23 to the right, and then 10 to the left. So you can do plus a negative 10, or you can do minus 10. That force is going to the left there. And that gives me 13 newtons to the right. It's a vector, got to include that direction. All right, now I'm going to sum the forces in the y direction. And I'm saying down is positive now. And the reason I picked that is just because there's a bigger number. In my brain, I won't have to deal with negatives. So that's what I like to do. 100 down minus 19 up. And that gives me 81 newtons. And it's a positive 81. So I look over here and positive is downward. Okay, so 81 newtons is downward. Okay, if this were northeast, south, and west, then it would be to the south. All right, so what's the overall net force? I've got the net force in the x direction and the net force in the y direction. So what's the overall sum of all the forces? The net force. Well, since I do have a right-hand component of 13 and a downward component of 81, then I can stack them together. The nice thing about right and down is they're perpendicular, and that's why we're picking out the x and the y components. It's because if we needed to, we could figure out the net force. I'll just extend that. Actually, let me actually draw a good arrow here. Right there. So this is the sum of all the forces right there. And how would you get that? Of course, with the Pythagorean theorem. So if I take the square root of 81 squared plus 13 squared, that's going to give me the magnitude of the net force. All right. So I'll take that square root 81 squared plus 13 squared is 82. Oh wow, that wasn't very far off, was it? All right, so just over 82, 82.04. Okay, I'll just say 82 newtons. All right, now that's the magnitude though. What about the angle? Well, if I plug in an angle right here, let's look at this angle reference. Then I've got two sides. I also have a hypotenuse now, but I do have the two sides. So the angle, I'm going to use the inverse tangent of opposite. So if this is my angle here, the opposite is 81 divided by 13. So I'll take the inverse tangent of 81 divided by 13. 80.88 degrees. I'll just call it 81 degrees. Wow, there's a lot of 81s in this one. So just to differentiate here, I'll call it 80.9 degrees. None of these are measured, so sig figs are not very useful at the moment. So we've got 82 newtons, 80.9 degrees. So to sum that up, I'm going to write 82 newtons at 80.9 degrees. What? 80.9 degrees what? Well, this is toward the south of the east direction. Okay, so this is the measurement here, and east is one of those standard directions. So I could also say 80.9 degrees downward from the horizontal. That's another weird way to say it, but since I didn't really have a starting direction here, I'll just say south of east. S of E, okay, is what that says. South of east. And that would be the net force of that crazy construction that I just made up in my brain. So here we had force diagrams from the conceptual perspective, what forces are acting on a body in which direction, and also from the numerical perspective. And yes, we will be combining both of these because objects with mass have weight, and that will affect the amount of normal force that the ground applies to them, which is going to affect the amount of friction that acts on them, which could affect the amount of thrust force required to accelerate that object. And I hope you see where we're going there, but I hope this was helpful.
Shut up and sit down.